Today we are going to discuss about applications of Bernoulli's equation. Right. What is Bernoulli's equation? That already we have discussed earlier. Application of Bernoulli's equation. Bernoulli's equation is applied in all problems of incompressible fluids where the energy considerations are involved. Now we shall consider its applications to the following measuring devices. Right? What are the devices? One is venturimeter, orifice meter, and pitot tube. What is venturimeter? Venturimeter is the device which is used to measure the flow rate in case of pipes. And another one is the orifice meter. Right. Orifice meter is also one of the device which is used to measure the flow rate in case of pipes. That means venturimeter and orifice meter, these two are the equipments used to measure the flow rate in case of pipes. And last device, that is pitot tube. Pitot tube is device which is used to measure the velocity of flow at a point in channels as well as in case of pipes. Right, these three devices we are going to discuss one by one. First we are going to discuss about venturimeter, derivation of rate of flow through venturimeter. Now we are going to take one diagram here. This is the pipe flow. This is the pipe flow. The pipe is carrying water from left to right. Here we are going to provide one device, that is the venturimeter. This is the venturimeter. Venturimeter having three components. One convergent part, and second one is the throat, and third one is the divergent part. Venturimeter having three parts: convergent, throat, and divergent part. Right? And also water is flowing from left to right. And also in this diagram we are going to take two sections, that is section 1.1 and section 2.2. Section 1.1 is taken over the pipeline before the venturimeter. Section 2.2 is taken over the or at the throat of the section. Section 1.1 taken over the pipeline and section 2.2 is taken at throat of the section. Now we are going to install one piezometer in the pipe. Because of the pressure in the pipe, automatically the liquid will move like this, raised up to this level. And also one more piezometer is also installed here at the throat section. Because of the pressure here, this is also raised the water like this. The level of water at throat is equal to up to this one. The level of water in the pipeline is equal to up to this one. This is the head. This is the head. There is a head level difference between at the piezometer level at the pipe and also piezometer level at the throat. That the head level difference is H. What is happening? In case of pipe, the cross-sectional area is more as compared with the throat. Therefore, cross-sectional area is more, automatically pressure head is more. But here cross-sectional area is less. What is happening? Velocity head is more. At the pipe, this is the pressure head. At throat, this is the pressure head. The level difference between these two is H. Because cross-sectional area is more, velocity is less, automatically pressure head is more. Here cross-sectional area is less, cross-sectional area is less, pressure head is less, velocity is more. Because this is based on the Bernoulli's equation. What is the Bernoulli's equation? Pressure head plus velocity head plus datum head at section 1.1 must be equal to pressure head plus velocity head plus datum head at section 2.2. Right, now pressure head is nothing but P1 by W plus Z1 plus V1 square by 2G at section 1.1. Pressure head plus datum head plus velocity head at section 1.1 is equal to P2 by W plus V2 square by 2G plus Z2. Pressure head at section 22, velocity head at V2 square by 2G, velocity head at section 22, datum head at section 22. This is the Bernoulli equation. Now, here the cross-sectional area is more, automatically velocity is less as compared at the third section or at section 22. Section 11 cross-sectional area is more as compared with the section 22. Automatically cross-sectional area is more, cross-sectional area is less here. Cross-sectional area is less means velocity head is more. Okay, automatically velocity head is more means definitely pressure head should be less. The sum of the pressure head plus velocity head plus datum head must be equal to the another section pressure head, velocity head, pressure head, datum head and velocity head. So that here the pressure head is more at section 11. Automatically velocity head is more at section 22. At section 22 pressure head is less. At section 22 velocity head is more. Datum head, because this is the horizontal pipe, datum head at section 11 is equal to section 22, Z1 is equal to Z2. These two are cancel. 1 point pressure head increases, velocity head decreases. Velocity head increases, automatically pressure head decreases. This is the continuity equation. This is section 11, this is section 22. Section 1 is taken over the pipe, section 2 is taken at the throat. Right? At section 11, P1 is the pressure intensity at section 11. V1 is the velocity of flow at section 11. D1 is the diameter of the pipe at section 11. A1 is the cross-sectional area of the pipe at section 11. Cross-sectional area A1 is equal to what is the formula? Pi D1 square by 4. D1 is the diameter at section 11. Therefore, A1 is equal to pi D1 square by 4. Now, at section 22, P2 is the pressure intensity at section 22. V2 is the velocity of flow at section 22. And D2 is the diameter at section 22. A2 is the cross-sectional area of the throat. That is equal to A2 is equal to pi D2 square by 4. D2 is the diameter of the throat. Right? These are the terms used in this diagram. Right. Now, already I have explained about the Bernoulli equation. Now we are going to apply the Bernoulli equation. What is Bernoulli equation? Just now I have explained to you. Incompressible ideal fluid, when the flow is steady and continue, the sum of pressure head plus velocity head plus datum head at one section must be equal to pressure head plus velocity head plus datum head to the another section. Right? This is the Bernoulli equation. Right now, assumptions. Already I have explained assumptions made in the derivation of the Bernoulli equation. That Bernoulli equation is derived from the Euler's equation of motion. Now, what are the assumptions we have used? That assumptions are, once again I am going to recall you. The assumptions are, first one, fluid is ideal, non-viscous and incompressible. Fluid is ideal, non-viscous, incompressible. And another assumption is fluid flow is steady and continuous. Fluid flow is steady and continue. And next one, fluid flow is irrotational. And another assumption, frictionless inner surfaces. These are the assumptions used in the derivation of the Bernoulli equation. That Bernoulli equation also we have derived from the Euler's equation of motion. Apply Bernoulli equation at section 11 and section 22. Right? This is the section 11 over the pipe. This is the section 22 at the throat section. At section 11, pressure head plus velocity head plus datum head at section 11 must be equal to pressure head plus velocity head plus datum head at section 22. This is the Bernoulli equation. Right here, P1 by rho g is the pressure head at section 11. V1 square by 2g is the velocity head at section 11 plus Z1 is the datum head at section 11. Okay. This is the direction of flow. This is the center line of the pipe. Right? That is equal to P2 by rho g is the pressure head at section 22. V2 square by 2g is the velocity head at section 22. Z2 is the datum at section 22. Right? But here the pipe is in horizontal. Pipe is in horizontal, therefore Z1 is equal to Z2. Datum head at section 11 is equal to datum head at section 22. Therefore Z1 is equal to Z2. Here these two terms are neglected. Therefore P1 by rho g plus V square by 2 V1 square by 2g is equal to P2 by rho g plus V2 square by 2g. This is the equation, Bernoulli's equation, if Z1 is equal to Z2. Now from this equation P1 by rho g, this is move this side, minus P2 by rho g is equal to V2 square by 2g, this is the moving that side, that is equal to V1 square by 2g. We have, this is the relation. P1 by rho g minus P2 by rho g is equal to V2 square by 2g minus V1 square by 2g. This is from this equation. Now P1 minus P2 divided by rho g, P1 minus P2 divided by rho g is equal to V2 square by 2g minus V1 square by 2g. This is the equation we have. But we know the pressure head difference between section 11 and section 22 is H. That means P1 minus P2 divided by rho g or P1 minus P2 divided by W is equal to H. H is the pressure head difference between section 11 and section 22. Therefore, in place of P1 minus P2 divided by rho g, we are going to take H. H is equal to V2 square by 2g minus V1 square by 2g. This is the equation we have. H is equal to V2 square by 2g minus V1 square by 2g. Right. H is equal to V2 square by 2g minus V1 square by 2g. Now we are going to once recall continuity equation. Continuity equation means Q is equal to A1 V1 is equal to A2 V2. That is the continuity equation. Suppose this is one pipe, this is section 11, this is section 22. The cross sectional area at section 1 is A1, velocity at section 1 is V1. Cross sectional area at section 2 is A2, velocity at section 2 is V2. As per the continuity equation, Q is equal to A1 V1 is equal to A2 V2. Already I have explained about continuity equation. Q is equal to A1 V1 is equal to A2 V2. Right? This is the continuity equation. From this equation, A1 V1 is equal to A2 V2. A1 means cross sectional area of the pipe, that is at section 11. V1 means velocity of flow at section 11. A2 means cross sectional area of the throat or at section 22. V2 is the velocity of flow at section 22 or the throat. Right? From this equation, V1 is equal to A2 V2 divided by A1. Are you clear? V1 is equal to A2 V2 divided by A1. Now, in the above equation, in place of V1, we are going to take A2 V2 divided by A1. Right. Therefore, H is equal to, H is the pressure difference between section 11 and section 22. That is equal to V2 square by 2g minus, in place of V1, we are going to take this value. That is A2 V2 divided by A1 square divided by 2g. Right? This is equal to V2 square by 2g minus A1 square V2 square divided by A1 square into 2g. From this one, V2 square by 2g minus A1 square V2 square divided by A1 square into 2g. Now we are going to take V2 square by 2g is common. V2 square by 2g is common. Then 1 minus V1 square A1 square divided by a1 square by divided by, sorry, this is a2, this is a2, right, a2 square divided by a1 square. This is the equation we have, right? Then this is equal to v2 square by 2g a1 square, then a1 square minus a2 square. H is equal to v2 square by 2g in brackets a1 square minus a2 square by a1 square. Now 2gh is equal to v2 square a1 square minus a2 square divided by a1 square, right? Now v2 square is equal to 2gh divided by a1 square minus a2 square divided by a1 square. This is equal to 2gh into a1 square divided by a1 square minus a2 square, right? Now v2 square is equal to 2gh into a1 square divided by a1 square minus a2 square, right? v2 square is equal to 2gh a1 square divided by a1 square minus a2 square. Now v2 is equal to square root of 2gh a1 square divided by a1 square minus a2 square. Therefore this is equal to cancel a1 divided by root a1 square minus a2 square into root, from this equation we have a1 by square root of a1 square minus a2 square into root 2gh. This is the relation we have. v2 is equal to now we know one equation. We want to determine the discharge flowing through the pipe, right? For that purpose, this is the equation we have. Q is equal to a1 v1 or a2 v2. Already we have determined v2, therefore Q, discharge from the pipe, is equal to a2 v2. v2 is nothing but, now we are going to substitute the value v2 already we have determined, that is equal to a2 into a1 divided by square root of a1 square minus a2 square into root 2gh. Now therefore Q is equal to a1 a2 divided by square root of a1 square minus a2 square into root 2gh. Now Q is equal to a1 a2 divided by square root of a1 square minus a2 square into root 2gh. This equation we have derived that with the reference to the flow is incompressible and ideal. The flow is incompressible and ideal. This is the equation we have. So that this equation is known as theoretical discharge. This equation Q is equal to a1 a2 divided by square root of a1 square minus a2 square into root 2gh is the theoretical equation because it is derived with respect to the incompressible fluid and incompressible and ideal fluid. Therefore the discharge, the actual discharge from the pipe is less than the theoretical discharge. Now we are going to introduce some coefficient, venturimeter coefficient here. Therefore this is the theoretical discharge, Q theoretical. Now actual discharge, Q actual is equal to CD into a1 a2 divided by a1 square minus a2 square into root 2h. This is the actual discharge. Actual discharge is equal to CD into a1 a2 divided by square root of a1 square minus a2 square into root 2gh. Right? Same equation here. Discharge Q is equal to Right, discharge Q is equal to A1 A2 divided by square root of A1 square minus A2 square into root 2GH. This is the theoretical discharge. So discharge under ideal conditions, therefore actual discharge is less than the theoretical discharge. Therefore actual discharge is Q actual is equal to CD into A1 A2 divided by square root of A1 square minus A2 square into root 2GH, where CD is the coefficient of venturimeter that should be less than 1. CD is the coefficient of venturimeter. The CD value should be less than 1. Right? The flow through the venturimeter or discharge through the venturimeter, Q is equal to Q actual is equal to CD into A1 A2 divided by square root of A1 square minus A2 square into root 2GH. Right? H is the pressure head difference between section 1 and section 2. Right? A1 is the cross sectional area over the pipe. A2 is the cross sectional area at the throat. Right? CD is the coefficient of venturimeter that should be less than 1. Right, thank you one and all.